All right, so we're very happy to have Simeon with us to tell us about the conformal field theory at large fermion charge.
Hi, everybody. So this talk, I'll be talking about some general themes that I've been working on for the last couple of years, but focusing on some recent developments over the last couple of years involving extending these ideas to large fermion charge. So, but I'll start by, for those of you who haven't heard a lot about the general story, this talk is about this general idea of the simplification of otherwise strongly coupled quantum systems in the limit of large quantum number, which I'll generically refer to as J. By otherwise strongly coupled, I mean outside of any simplifying limit where the theory becomes semi-classical for other reasons, or maybe in a simplifying limit, but with the quantum number taken so large that the system behaves differently than you might have expected, despite being weakly coupled. So the primary question in such a talk is, is this even a subject? Why is this a subject at all? Yes, it is a subject. In some sense, it's an old one. Many examples have appeared in the literature going far back into the past. The general idea can be thought of as a kind of modern systematic application of the old idea of the correspondence principle, going back to the early days of quantum theory. And for whatever reason, it wasn't until relatively recently that these ideas were kind of systematized and used to study theories of modern interest, like strongly coupled conformal field theory and quantum gravity, and so on. But the basic idea being that at large quantum number, you expect low-lying states to be semi-classical, because the large quantum number is the only thing in such a limit that can appear in the denominator of the Lewis. So right, the idea really goes back to prehistory, the atomic hypothesis, jumping ahead a couple of millennia to the correspondence principle, large spin in the hadron spectrum, limited thermodynamics, and then slightly more modern history. The idea was sort of applied to theories of kind of modern interest to string theorists and quantum gravitists by Bernstein, Maldacena, and Nastase, and then many people followed up on these ideas in string theory, and then many ideas of this kind were for the case of large spin in a single plane anyway, were applied, proven directly from light cone bootstrap, applied to hadronic systems, and then here's some references in the more modern era. Actually, too many to include. A lot of interesting stuff, and some applied to cases with extended supersymmetry, which I'm not going to talk about today for lack of time. And then a huge set of references that I can't do justice to, and then even more stuff in the last couple of years, which I've fallen behind on reading. But so, what is it for? What is the large quantum number expansion for? It's to answer the same kinds of questions as the conformal bootstrap, at least in the case when there are global symmetries present, which is to systematically and efficiently analyze quantum field theory and practice usually conformal theories that have no exact solution in terms of explicit functions. We all like to know, sort of in general, what does theory space look like? What is the large-scale structure of QFT and CFT theory space? An extremely consequential question for many areas of science, through the string theory connection for the most part. So how do we do this? Well, back in the old days, people superstitiously thought that maybe generic conformal field theories were always integrable. This is really not true. It's very not true. But we've developed some techniques to analyze strongly coupled conformal theories. The most modern and prominent one being numerical bootstrap. So direct numerical bootstrap methods are already extremely efficient, remarkably efficient anyway, power law in the number of operators. But since the number of operators tends to grow exponentially with the dimension of the operator, or with central charge or other quantum number, in any sort of extreme limit, it becomes an exponentially growing problem. So it's not it's still not tractable to attack generic amplitudes in generic theories with direct numerical bootstrap. What's interesting is that all known extreme limits appear to have simplifying behaviors in I think all known circumstances, or maybe there could be exceptions, but I don't know. This is broadly a generalization of the notion of duality. At least that's sort of the point of view I'm going to take. Now, in the case of large spin in a single plane, conformal bootstrap has attacked this limit very efficiently because of the fact that the conformal blocks themselves carry that kind of quantum number. But for other quantum numbers, it doesn't work that way. Even as simple a modification as large spin in multiple planes, indeed greater than or equal to 4, there's no known analytic method, analytic bootstrap method. The same is true for internal global symmetries of various kinds. So in many cases, limits like that are accessible to new kinds of effective field theory in regions where bootstrap methods slow down. And there's excellent agreement, well, more than just one now, for a few predictions where bootstrap and these EFT methods overlap. So where does that leave us? What do we hope to accomplish? Well, we could be modest, grandiose, or somewhere in between. Most modestly, we could just try translating EFT behavior into bootstrap data and say what it means for bootstrap data and give a sort of target or numerical or other sorts of analytic bootstrap to be able to hit. That's the most modest goal. The most grandiose goal would be to actually derive these sort of EFT behaviors directly from the bootstrap equations and solve everything in every limit where the direct numerical methods break down. Or you could try doing something in between. So the grandiose goal seems to be very much out of reach, not just to me, but I think to almost everyone. Nobody seems to have any ideas at the moment how this could be accomplished. There is one extremely interesting but so far isolated result on this intermediate approach, and so I'm going to talk about the most modest possible. So just for some introductory context, unless many people have seen this before already. Okay, in that case, I'll talk a bit about this. So the most vanilla possible conformal field theory you could find with a continuous internal global symmetry is the Wilson-Fisher O2 model in 3 dimensions at large O2 charge. Okay, so this theory has no adjustable parameter. It was discovered by working in the epsilon expansion and the large n expansion and extrapolating. Now there's extremely good evidence that it exists. We know, the critical exponents for the low-lying operator is a very good approximation, but still not good enough. There are many things we don't understand. In particular, charged operators are very ill understood. What's the dimension of the lowest charged operator at large J? So this is a theory with no no control parameters at all, unless you want to sort of vary the space-time dimension or the rank of the symmetry group. But even in those families of theories with control parameters, going to large O2 charge makes all of those sort of perturbation theories break down. So the first thing I want to get across is that large global charge really is a kind of, large quantum number in general really is a kind of duality. It conflicts rather than cooperates with other forms of perturbation theory. So so we really need, and also it seems conflicts with sort of the simplicity of the bootstrap. Bootstrap methods for tackling these operators slow down extremely fast in the limit of large as the charge gets larger. Okay. So how do we attack this? We can translate this question into radial quantization, into a question about the energy of the lowest state of charge J on a unit S2, and then perform a kind of renormalization group analysis from the UV completion of the theory to the conformal point in the presence of a finite density, down to the lowest energies defined by energies of order 1 in units of the sphere. And there's a sort of direct renormalization group analysis revealing that the low-lying large charge sector is described by an effective field theory of a single compact scalar chi, which can be thought of as the phase variable of a complex scalar phi in the canonical UV completion of the O2 line. So the leading order Lagrangian of this effective theory is extremely simple. The leading order Lagrangian is just B times the absolute value of the gradient of chi to the third power. This is in 3 dimensions to see that this is scale invariant. So this is really an incredibly simple effective theory. It's literally the second simplest Lagrangian you can possibly write down. The simplest Lagrangian in the world is a free massless scalar whose Lagrangian is grad phi squared. Well, this is the second simplest Lagrangian and it's grad chi cubed. It's literally that. With some subleading terms, but those are less relevant at large charge, and so I'll explain that in a minute. That coefficient B is not something we know how to compute analytically, but the simple structure of this EFT has sharp and unexpected consequences. So the immediate consequence of the structure of the EFT is that the lowest operator is a scalar of dimension some number constructed out of B to the 3 times J to the 3 halves. So already we learned something kind of non-trivial about the scaling of the leading of the lowest operator dimension with the charge. So questions so far?
This Lagrangian doesn't allow for perturbative expansion around
Oh, it does.
To 0.
The perturbative expansion is in the charge itself. Right. So you never expand around the vacuum of this theory. It's only meant to be expanded around around a large charge, and so around that vacuum, there's no you don't see the non-analyticity at 0. A good sort of intuitive guide is just the Nabu-Goto action. It's the same kind of thing, right? It's only meant to be expanded around around a state where this Goldstone has a large expectation value. So the leading order EFT predicts more than just the leading power law. It predicts a lot. Because the quantum loop effects in the EFT are suppressed at large J, so the EFT can be quantized as a weakly coupled effective action with effective loop counting parameter J to the minus 3 halves. So for instance, you can compute the entire spectrum of low-lying excited primaries. The dimensions, spins, and degeneracies of the excited primaries are those of a Fock space of oscillators with spin L of L greater than or equal to 2. And those just come from the spin 2 and higher harmonics of this of this phase variable chi expanded around the large charge vacuum. So the propagation speed of the chi field is equal to 1/√2 times the speed of light. That's not an input. You just give chi the appropriate bev, expand in bev plus fluctuations, and then the Gaussian term is forced to have that propagation speed. So the frequencies of the oscillators are 1/√2 times root L times L plus 1, with L greater than or equal to 1. So I said only L greater than or equal to 2 shows up in the spectrum of primaries, and that's because, well, the L equals 1 oscillator is also present, but exciting it only gives descendants. The leading order condition for a state to be primary is that no L equals 1 oscillators are excited. So exciting the L equals 1 oscillators just gives you the entire spectrum of descendants of the lowest level. So for instance, the first excited primary of charge J always has spin 2 and dimension of the lowest scalar operator plus √3, plus corrections that are subleading J. So even just this leading order theory is extremely predictive before adding even any quantum effects or higher derivative terms at all.
Sorry, Simeon.
Yeah.
A very naive question, since I'm not very familiar. This speed of the particle, is it physically acceptable, or is it okay for the theory?
I mean, it's true. It better be physically acceptable.
So does it correspond to some mass? I thought, since
No, it's massless excitation. 1/√2 is the sound speed. I mean, it's a Lorentz breaking state because there's a finite density. So it's not. There's no. I mean, if it was greater than 1, that would be a problem, but
Sure.
it's not. So subleading terms can be computed as well. I've just given the leading order expressions for everything. And these depend on higher derivative terms in the effective action with powers of grad chi in the denominator. And these terms have a natural kind of hierarchical organization in powers of the charge. So at any given order in derivatives, there are only a finite number of such terms. And as a result, at a given order in the expansion, only a finite number of terms contribute. So, and obviously there are far more observables than there are effective terms. So there are an infinite number of theory-independent relations among terms in the asymptotic expansions of various observables. So it's a very predictive theory. So the gradient cube term is the only allowed term allowed by the symmetries at order j to the 3/2, and there's only one other term contributing to the non-negative power of j, and it's this thing. So for us, the interesting part is this. It's 1 power of grad chi times the Ricci scalar times some other unknown coefficient. And in particular, there are no terms that scale as j to the 0. There's no term you can write down which has that scale. So that means that the j to the 0 term in the expansion of the operator dimension is calculable independent of any unknown things about this vector Lagrangian. It's independent of the Wilson coefficients. It's like the square root of 3 in the gap between the large charge ground state and the first excited primary. So specifically, the formula for the operator dimension up to order j to the 0 is this c sub 3/2 term coming from the leading term, coming from the gradient cube term, c sub 1/2 term coming from this subleading term I just mentioned, minus 0.093726 and so forth. So that's that term comes from one loop, and there's no conformal counter term that renormalizes it. So it's just some calculable. Yeah.
How can you compute the scaling dimensions delta j from the Lagrangian?
What's that now?
So you just literally quantize it around the large charge ground state.
So in the path integral,
Or canonical quantization, however you want. I mean, there's no.
and this correction there is a numerical result.
It's a one loop. It's a one loop.
I want so first order in this expansion.
I don't know. It depends how you count orders, but it's one loop. Okay. Yeah. And there are no contributions from higher loops because j to the minus 3 halves is the loop suppressing code. And so, right, so some terms are calculable, some terms are Wilson coefficient dependent. Differences between operator dimensions are very calculable because the same Wilson coefficients contribute to all of them.
Does that number has a nice integral representation?
Well, I would say it's pretty nice, but it's not so nice that we got it right in the first draft. It's just a zeta function, and one person in the collaboration miscalculated it. I'm not going to say who that person was. Yeah, it was. Anyway. But yeah, I mean, it is simple for a capable graduate student and maybe even a talented undergraduate. It's just a zeta function.
So these coefficients C are also known functions in terms of B, even though you don't know.
Yeah, that's right. They just come directly from the Wilson coefficient. Okay, so this universal term and other large J relations in the O2 model don't have any fudge factors or adjustable parameters. Given the identification of the universality class, these values are universal and absolute. And similar predictions have been made for OBE coefficients, a lot of interesting stuff you can do. So I think for the rest of this talk, what I'm mostly going to focus on is, well, first I'm going to tell you how difficult it is to get away from this universality class. So after first applying this analysis to the O2 model, you begin to realize that it's very robust, that almost no assumptions go into this calculation, and that turns out to be a problem because you really would like to find some theories that don't have this universal behavior at large charge. Most of them actually do. But there are a few that don't, and I'll talk about that in a bit. But first, let me address some.
Simeon,
Yeah.
that's a question about just the previous slide. So the result is just for scalar operators. What is the Spain? What the information was?
Oh, it's a result. So it's a result for the lowest charged operator overall, which as an output is a scalar.
Yes.
Right.
Is the analogous formula known for the Spain guys? The large charge limit?
You mean large spin and large charge?
No, say just
Sure.
other one spin and large charge.
Yeah, like for spin 2, the lowest thing is the spin 0 dimension plus √3.
I see.
For you just add
The simple relation.
You just add some phonons, yeah.
And it's just scalars, they're all singlets. I mean, up to complex conjugation. What about the degeneracy of this large?
Well, so what about the
degeneracies?
There's no degeneracies. Or I mean, sorry, degeneracies.
It's just complex. It's a complex operator. Up to its complex conjugate.
Yeah, I mean that's right. And of course, there are approximately degenerate ways you can make approximately degenerate things by adding phonons in different ways. But remember, they're not integer. They're not integer frequencies. There are these algebraic numbers.
Yes.
So you don't even have exact degeneracies from those. You have an entropy, but you don't have any exact.
But it's a special, like the density of states. No?
The density of states is just that of a free field theory of one boson. Until you start hitting the cutoff. So the UV scale here is just given by the chemical potential, which is the square root of the density, and so up to that energy, it's just given by just the states of this free scale. So it really is, I mean, once you identify the universality class, it's just like kind of boring, like effective field theory stuff. The interesting things are that A, it's an effective field theory that for some reason wasn't written down until like extremely recently. Like, you know, when I was a grad student, I heard, oh, you know, there are no more effective field theories. They're all, you know, classified by CCWZ. And, you know, in fact, these sort of large charge effective theories have been CCWZ-ized, but it turns out that you wouldn't just like randomly discover them. You have to apply lots of constraints, and you have complicated combinations of Lorentz breaking and internal symmetry breaking that make you do all sorts of complicated things. But yeah, once you identify the EFT, it's sort of boring physics, except it describes a lot of things successfully. So I'll talk about that in a second.
Yeah, just a very native question. Since the power is bigger than 1,
Which power?
the J to the treehouse.
Yeah.
Treehouse is bigger than 1. So if you take 2 operators, you know, with charges J1 and J2, that up to J, and sort of fuse them or something, what happens?
You have a very soft power. I mean, you have a large suppression of the OPE as you take the operators towards each other. You have a large positive power of X. And same thing happens, by the way, in two-dimensional theories. You can see this in the Cesar representation. In free fermions in any dimension, it's the same thing. So we're smashing 2 Fermi surfaces into each other, or you get a lot of zeros from all the fermion wave functions. But it's more universal than that. So, okay, you might think that there's something weird or inconsistent or uncontrolled about a Lagrangian like grad chi cubed. So I'm going to anticipate some frequently asked questions, some of which did come up sort of a little bit obliquely. Okay, so isn't this Lagrangian singular? It's a non-analytic functional of the field. So when you expand around chi equals 0, you get ill-defined amplitudes. But yeah, I mean, as I said, you're not supposed to use the Lagrangian there. It's only meant to be used around the large charge vacuum. Which at large J is just the classical solution, chi equals mu g. So chi is linear in time. Mu goes as the square root of the density. It's just the chemical potential. And rho is del L by del chi dot, which is chi dot squared. So chi dot, which is mu, is rho. So the expansion into Bevan fluctuations carries a suppression of inverse chemical potential for each fluctuation. So there are many well-known effective actions that behave this way. This particular one was studied a lot at Year 1U. Some progress on that decade. Next question. Isn't this effective theory ultraviolet divergent? That means that loop corrections are incalculable and observables are meaningless beyond leading order. Okay, but that's not true either. This is a very phenomenologically savvy department, so you all know how effective field theories work. You quantize it in the limit where the loop corrections are small. You can, since there's a hierarchy between the UV scale set by the density and the IR scale set by the size of the sphere, you can always wedge a third scale parametrically larger than one and smaller than the other and let that be the cutoff scale. Then loop divergences are under control, and you can regularize and renormalize the theory with all within perturbation theory. And subtract off all cutoff dependent terms. But say, wait, don't the counter terms ruin everything? Don't they render the theory incalculable? No. As usual in EFT, the counter term ambiguities of subtraction correspond one-to-one with terms in the original action allowed by symmetries, and I just told you that there aren't very many of those up to and including any given order in the expansion. And at some orders, there are no ambiguities. Okay. So next question. Wait, are you saying that every CFT with a conserved global charge has the exact same asymptotic expansion, but here's a counterexample, then blah 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 blah. Some theory I didn't say anything about. Right, so I didn't make any claim that broad. The RG analysis applies to many but not all CFT, and I'm going to get to the ones which it doesn't apply to at the end. And more generally, CFT can be organized into these large charge universality classes. So for instance, free complex fermions or free complex scalars are in different large charge universality classes. They have a different behavior, can also be analyzed, of course. The large J universality class of the O2 model contains many other interesting theories which have been investigated in the meantime. Large CPN, the CPN models at large topological charge, some superconformal theories. I'm going to talk about this a bit. And then many other interesting universality classes in 3 dimensions, like large Noether charge in the higher Wilson-Fisher ON models and UN models, the CPN models, higher Grassmannians, large baryon charge or large monopole charge, and Chern-Simons matter theories. I'm going to mostly stay away from non-abelian symmetries. When I talk about theories with large non-abelian symmetries, I'm still only going to activate a sort of diagonal U1 in symmetry groups. You can also study other you can study large representations of whatever large representations you want, and those can be analyzed within the same sort of EFT analysis. But then the classical ground states often become quite complicated in those cases, so I'm going to stay away from that today. That's a whole other talk. But so before going on, I want to talk about some evidence for this picture of large J self-perturbatization of strongly coupled theories, starting with the prediction for the O2 model, where we predicted this formula with this interesting universal coefficient. One wants to compare with bootstrap calculations in the O2 model, but at the moment, bootstrap methods have only been able to reach rather low values of J with any precision. The state of the art, by the way, has improved, but not that much. So there are now results for J equals 4 that are like okay, but anything above that has been completely inaccessible for the most part. But not necessarily forever. So it would be interesting to develop that further. But the first really non-trivial confirmation of these predictions came from a Monte Carlo analysis up to J equals 15 in the O2 model, independently computing charged operator dimensions and estimating this leaving the Lagrangian coefficient. And so one striking thing is that using these data points to these high data points to estimate the unknown Wilson coefficients to reasonable accuracy, the curve, the theory curve represented by the first 3 terms in the asymptotic expansion runs almost perfectly, not only through J equals 2 and J equals 1, but even through J equals 0 as an output, not as an input.
Is it robust by a linear equation?
But there is no.
It's not a fit, it's theoretical.
Yeah.
There is no. So precise bootstrap results only exist up to say J equals 2. But yeah, with these EFT parameters calculated from Monte Carlo, you can compare, and the comparison is exact to like 3 significant digits.
So is there a general reason why this large G expansion is not asymptotic? Because that clearly looks like that, right? So
Oh no, I think it's asymptotic.
it is asymptotic.
I'm pretty sure it's asymptotic. It's just that the radius of convergence, or of approximate convergence, is good enough that you don't, that the errors are very small. Probably the maximum accuracy is going to be like e to the minus 2 pi cubed or something like that. But it's the 2 pi's that help you.
But it looks like you're saying it works all the way down to j equals to 0.
Well, with an error of about 1%, roughly 1%. Depending how you define it. There's some arbitrariness in how you do that extrapolation, but depending how you define it, it's like a percent level.
And is there any understanding of non-perturbative correctness in J?
In supersymmetric theories, we have an extremely good understanding of it. And I think the lesson one learns from that is that, the expansion is almost certainly only asymptotic with the pole in the Borel plane controlled by the mass of the lowest non-Goldstone excitation. So certainly in the supersymmetric case, that's exactly where these exponentially small corrections come from. And there's been also work in non-supersymmetric examples by Orlando, Kalogerakis, Dondi, Reffert, and possibly some other people on.
That's in the context of O2 models?
In the context of the ON models, maybe using large N as a second control parameter. I don't remember exactly. So in fact, before getting to non-relativistic CFT, let me stop sharing this one, start sharing the other one. Okay. No, I'm not gonna.
You want to share your iPad?
I'm gonna share. I'm going to do it. Share screen. We can do that. Start broadcast. So. Yeah. So good. Okay. Is that awesome? So far, we have discussed examples in which all the charge at every step of the RG flow defining these theories are carried by bosons. But there are many quantum theories in which the interesting quantum numbers are all carried by fermions. So examples include the standard model in which the lepton, baryon, and flavor quantum numbers are only carried by fermionic fields. The standard model is not a conformal theory, but examples exist in CFT as well. So I'm going to start by introducing some CFT with internal symmetries carried in part by fermionic degrees of freedom, and also some CFT with global symmetries where some quantum numbers are carried only by fermionic fields. So the first case is a supersymmetric theory with 4 real supercharges, which is the dimensional reduction of n equals 1 supersymmetry in 4 dimensions. So at the conformal point, there are an additional 4 superconformal generators as well. So this theory can be thought of as starting in the UV with a single chiral superfield phi. A lot of young people in the audience, I don't know, maybe some of you don't know what supersymmetry is or chiral superfields are. Well, I guess it would like think of that. But do you need to do a quick review of supersymmetry? Say supersymmetry. Schematically, you have commutation rules where supercharges spinorial charges anti-commute onto energy momentum and onto other things as well. Also onto lowering operators when conformal. Also, R charges, Q, which are just things which rotate the supergenerators of the things. I think this is all I need to tell you about this for the purpose of it. No. So Q. Supersymmetry obviously organizes fields into multiplets of unequal spins, because unequal spins and R charges, because the supergenerators themselves carry both spin and R charge. So I think that's all I need to say, at least temporarily. A superpotential and Kähler potential are just ways of specifying the potential and kinetic term in a supersymmetrically covariant way. So the theory flows to a fixed point in less than or equal to 4 dimensions with a coupling of order d-4 near 4 dimensions. So going over to the free theory in 4 dimensions, just like the Wilson-Fisher models, the Ising model, and so forth. The only internal symmetry of this CFT in less than 4 dimensions is the U1 R charge, which I just mentioned on the last page, under which the boson in this supermultiplet has charge 2/3 and the fermions charge negative. So these are the R charges of the cubic supermodel. So this model is interesting because it illustrates a general principle that holds with some exceptions for finite charge density ground states. So, and this principle is a problem if you want to study something interesting. If there is any bosonic field at all that is charged under the global symmetry Q, then the ground state at finite Q density spontaneously breaks the Q symmetry. This is essentially impossible to get away from. So it has some exceptions and loopholes, but it's robustly true under generic conditions. The basic idea is as follows. For any theory with a U1 symmetry and a Lagrangian description, the ground state is what we would call helical, even if the theory is strongly interactive. So any theory with a Lagrangian description, not necessarily a weakly coupled one, just any description whatsoever in terms of a cutoff, a theory with a cutoff and arbitrary higher derivative operators with coefficients in units of the cutoff. For any such theory, the classical ground state always has this symmetry, which we call a helical symmetry, under a combined time translation and internal symmetry rotation with respect to some generator mu. This is just a fact about classical mechanics. It can be understood in various ways. It's applicable to any Lagrangian for bosonic fields. Always. There are many ways to prove it. The simplest is to just Legendre transform a finite density to finite chemical potential, and then find the ground state at fixed chemical potential mu, which must always be static. Right? So the ground state of any time independent Hamiltonian is always static, and then you can perform a time dependent gauge transformation of the background gauge field to remove mu, to set the background gauge field to 0, and that turns the solution helical because it's exactly a time-dependent gauge transformation that changes a static solution into helical.
So for instance, isn't the fact that this ground state is homogeneous, is that an assumption here?
No.
Because you may think that finite charge density, like some striped phase would be preferred one, right?
There are a lot of things you can imagine.
And
A striped phase may or may not be preferred, but the ground state still has the helical property regardless.
so it will have helical property, but it will be described, if it's inhomogeneous, then it will be described by different EFT, right?
Right. Yeah, by a different EFT, but no assumption about the nature of the EFT has been included in this. I didn't assume anything about the field content. Just that it had some bosons below the cutoff that transform into the symmetry. That's it.
You mean to argue with this helical thing?
Yeah, that's right.
But in your decay cube theory, they assume that it's
No, that still wasn't an assumption. I'll get to that. I'll try to separate what's assumed from what's derived. I think there was a lot of confusion about this at some point. Not our confusion, but a lot of confusion.
Sorry. Yeah. This argument was at the classical level. Do you have also an argument with the quantum?
I'm coming to it.
Okay. So
Yeah. But I didn't make any argument yet at the quantum level. But in the absence of other internal symmetries, genericity just dictates that the overall U1 phase of the fields is the only surviving light degree of freedom. So the next issue is just genericity. Absence of other symmetries, including maybe even accidental symmetries at large charge, assume for a moment that there are no such. Then it's just completely generic for the other degrees of freedom other than the overall phase variable to get maxed out.
But so yeah, it's related to what I was asking, because essentially you're saying that you assume that it's generic to get superfluid. But,
No.
But if
No.
translation variance spontaneously broken, there will be also phonons,
you're
right?
I'm allowed to not assume what you're telling me I'm assuming, and I'm not assuming.
But I think that's what this
No.
slide says.
No, there's a confusion here between phases and effective theories. They're not the same thing, right? This is important. The phase isn't directly derived from the field content of an effective theory. There can be strongly coupled dynamics within the effective theory that change the far low energy content from whatever it is at the scale just below the cutoff. This is telling you what happens just below the cutoff, if you like. There may or may not be strong coupling in this theory.
I'm not sure if it's related to what but I'm more asking about the statement that that's the only surviving light degree of freedom. Because if there is spontaneous breaking of translation invariance, there will be also phonons, right?
To have spontaneous breaking of translational invariance, you need some light degree of freedom to break it.
Well, it's the other way around.
No, it's not.
If there is spontaneously broken symmetry, it implies that there will be light degrees of freedom.
That's not how it works, though. Unfortunately, that's not how it works. Fortunately or unfortunately. If you have only massless degrees of freedom at the scale lambda, other than this phase variable, you cannot write down. An effective Lagrangian that has whatever, that has a translational invariance breaking ground state. There is no Lagrangian that accomplishes that if all the other degrees of freedom other than the phase variable are massive.
I think we are saying the same thing.
Okay. If you like, you can say that it's. If you like, you can say that it's an assumption about what's going on right below the cutoff, but I mean it isn't. Okay. I mean we can talk about it later, but I don't think it's really circular. I think it's actually just. But I mean, oops. I can tell you, or I'm going to get at the end, which will not be too much longer from now, to a case that really exemplifies the difference between these different things. Okay. but just to make it sort of clearer, if there is a field of U1 charge, of unit U1 charge, right, the phase variable, you define it as the imaginary part of the log of phi, and then the lowest energy classical solution just always has chi dot equals mu equals constant, and all other fields can be sort of gauge invariantized just by stripping off the phase. You're adding a compensating phase. Generically, all the neutralized bosons have 1-point functions of order mu to the delta and masses of order mu, and they can be integrated out. You're just left over with the phase variable. Okay, so there's some genericity assumption here. If there's even one charged boson below the cutoff scale with less than with a mass of mu or less, then we expect the U1 symmetry is spontaneously broken, and the low energy theory insists that of the phase. So this principle applies equally well to fermions as bosons. If there's even one light enough charged boson in the theory, then its phase can dress the fermions to neutral objects, and then these sort of neutralized tilted fermions can get masses of whatever kind, Majorana, Weil, Dirac, without violating any symmetries at all. So even with one boson that's light enough in the theory, we expect fermions are always gapped and always irrelevant to large charge physics. So that's kind of boring, right? The challenge is really finding something that doesn't behave this way. Yeah, the principle doesn't apply. There are various circumstances under which it doesn't apply. When bosons are charged under the U1, when there aren't any, or when all charged bosons are parametrically heavier than this scale. And then it can also fail when there are other symmetries keeping things light, either microscopic or emergent. But still applies pretty broadly. But we like to sort of try to get away from it. And okay, this is too long, but even when there are larger symmetries, there's a sort of version of this argument that gives another sort of simple large charge EFT for non-Euclidean symmetries under generic conditions. But for theories with a small number of degrees of freedom, you can even infer the large charge theories in the minimal universality class without appealing to genericity. Sometimes there are just too few fields to accommodate any possible breaking pattern, either for the U1 theory or the higher O2 theories. Involved in all these analyses is the Browner-Murayama-Watanabe theory of massive goldstones in spontaneous symmetry breaking, where the Lorentz symmetry and internal symmetries are broken spontaneously by the same order parameter. So in such cases, the counting of goldstone bosons differs from the relativistic case. So you can have up to as little as half of the conventional number of goldstone particles with the positively charged ones, the positively charged broken generators corresponding to massive goldstone bosons with non-relativistic dispersion relations, and the neutral ones corresponding to massless bosons with this speed of sound that's 1 over root. So this has interesting implications for the cubic supermodel. This is another case where you can really prove that the theory lies in the generic universality class. Since there's a charged boson with charge 2/3, there must be a spontaneous breaking of the R symmetry, having the classical helical ground state solution chi equals mu t. And then these neutralized fermions get a mass, but in this particular case, the mass is completely universal, not just universal in scale, but its coefficient is exactly fixed, independent of your choice of higher derivative terms in the effect of Lagrangian. So it holds regardless of all that. And that's because the super Poincare and super conformal generators with positive R charge create massive Goldsteiny, whose mass is precisely given by the supersymmetric extension of the Browner-Murayama-Watanabe massive Goldstone. So the generic situation, quote unquote, in the presence of a charged boson can actually be proven to apply in the cubic supermodel without appealing to genericity. So this generic low energy behavior is probably true in more general theories with at least one charged boson, but it's hard to prove without additional tools. I don't really have time to describe the additional tools, so I'll just say, even though conventional perturbation theories conflict with the large charge expansion, there is a clever trick called a double scaling limit that allows you to interpolate between conventional perturbation theory and large J perturbation theory. So in those cases, we have actual tools to compute the finite density phase structure. And when a charged boson is present, we can confirm the generic behavior and also extend our understanding to the cases without any charged bosons. So when using large charge methods, we have to be careful about using other perturbative parameters because the perturbation theory, conventional perturbation theory breaks down when J is much larger than the other inverse loop counting parameters. But there's a trick that allows us to interpolate. So if G squared is any kind of perturbation parameter, like a Yang-Mills coupling or minus dimension in the epsilon expansion or 1 over n or something like that, then there is an expansion where you hold the ratio of loop counting parameters fixed at lambda. So G squared J you hold fixed at the what I'll call the double scaled coupling lambda. And then taking J to infinity with lambda fixed, the theory is uniformly under control for all values, all fixed values of lambda, with 1 over J acting as a uniform loop counting parameter. So at small lambda, you should think of J to the minus 1 as really lambda over J, which is G squared. So the perturbation theory is under control for the usual perturbative reasons at small lambda. At large lambda, the non-Goldstone fields go to large mass, and the theory flows to some large J EFT description. So in some precise sense, moving from small lambda to large lambda is a renormalization group flow from small to large chemical potential, but the flow can be understood purely classically, since large J keeps the theory under semi-classical control as lambda changes. So there could be transitions or whatnot in more complicated theories, but if so, you can see them semi-classically in lambda. So this double scaling analysis has technically all the same ingredients as conventional perturbation theory, just expanded around an alternate saddle, and with 1 over J acting as the loop counting parameter. So all of these smart people developed it over the last few years. And so I'll just give, for want of time, the results of these double scaling analyses for theories with fermions and no supersymmetry. So starting with theories where bosons and fermions carry the charge. So there are these UV-safe so-called gauge Yukawa theories studied by Rolando, Reffert, and Simeon. These have fermions and D equals 4. They're a lot like QCD, but with a chiral flavor group, a color group, like the fermions in QCD-like representations, and then a sort of explicit additional fundamental pion field transforms like a pion, but it's an additional scalar. And it's under large N control in the Veneziano limit with NF over NC fixed and tuned to make the beta function small. So in this limit where epsilon is NF over NC minus 11 halves, and then you have these double scaled versions of the gauge coupling and Yukawa coupling, those double scaled versions held fixed while the Veneziano limit is taken. And in this limit, there's a controlled fixed point. The finite density behavior is calculable, And at large baryon number, the EFT is, as one would have expected in this baryonic, spontaneously broken baryonic symmetry phase, where chi is just 1 over n in log det. So this sort of is a nice test of these genericity assumptions. In other gauge Yukawa theories behave similarly. I won't do all those cases. But now you can repeat the same type of analyses for some simple, purely fermionic CFTs. And, well, I put it in quotes for a reason that's too long to talk about. Okay. The two cases we studied were the Nambu-Yona-Lacinio model in d equals 4 and the dimensional reductions to below d equals 4, which have this Lagrangian kinetic term, g over n times 2 for Fermi interactions, one with a chirality matrix inserted, the other without. There is a U1 vector-like and UN vector-like and U1 axial symmetry. And then also you can study the almost identical Gros-Neveu model, which just doesn't have the second term. So both have dimensional reductions with non-trivial fixed points. Oops, this should say d less than or equal to 4. And the Gros-Neveu model has symmetry, slightly different symmetry, d less than 4, slightly enlarged. So the main result is that despite similarities, there's a big difference in behavior. So at finite density, for the overall axial charge, the NJL model Cooper pairs, condenses, and spontaneously breaks the U1 axial symmetry at leading order in 1 over n. So it becomes just this same large charge universality class. The fermions are gapped, the U1 is spontaneously broken. And the Gros-Neveu model doesn't. This theory does not have a conventional double scaling limit. It's not described, at least in 1 over n perturbation theory, by a condensate, but by a Fermi surface. And now, speculative remarks, which will be verbal only, because I don't know for a fact that anything else I will say is true. But I want to, well, the thing which is definitely true is that these two models illustrate that this sort of almost inevitable flow into the same large charge universality class really isn't universal. It depends on the field content of the theory in exactly the way that you would expect. We tested it in some of these cases where there are charged bosons and found exactly as you'd expect. The fermions are irrelevant, and the charge is all carried by the bosonic field in the ground state. But in the purely fermionic models, it really depends on details. Some models spontaneously break the symmetry at leading order in the weak double scaling parameter, and then, which is to say the NJL model and related models. And in the Gros-Neveu model, which is very similar, does not do that. To all orders at weak double scaling parameter, it has a ground state that's a Fermi surface. But this is where I want to illustrate the difference between field content and phases. There are strong coupling dynamics within the Fermi surface EFT. And we believe that if you look at exponentially small corrections at large double scaling parameter, you will see again condensation, Cooper pairing, and spontaneous breaking of the diagonal U1 symmetry inside the UN cross UN. So that part is not yet proven, but if it is, it will illustrate an interesting point about these behavior of these sorts of models. So I'll end there and take questions.
Question. So when you make these statements about Gros-Neveu and Gros-Neveu-Yukawa, right, the Nambu-Jonas-Lacinio, were you working in epsilon expansion?
No, so we're working in large N. Work on the epsilon expansion is proceeding with myself, Orlando Repper and Versini. And it seems, well, I didn't ask them if I was allowed to say. So maybe they'd get mad at me if I said. But it doesn't look like the situation in the epsilon expansion is any different. It looks like probably Fermi surface to all orders in double scaling parameter. We're now, by double scaling, we're talking about epsilon j. And possibly, I think, exponentially small corrections spontaneously breaking the symmetry with condensation. So when I said I wanted to distinguish between field content and phases in the EFT, that's an example which clearly distinguishes the two. The EFT contains fermions and no bosons at the cutoff scale, and you have to go exponentially far down to see what the actual phase is. But that's calculated by strong coupling effects in the infrared within the EFT itself. These other examples, there is no strong coupling in the EFT. It's just right. It's derivatively coupled. It's weakly coupled in the infrared. So there's no. So in those cases, the field content immediately does dictate the things, but not in all cases.
Can I ask whether the generalizity argument you were mentioning that is meant to be valid only at large charge, or whether you have in mind?
Right, yeah, I mean, right. So this is always at large charge where the chemical potential is the largest scale in the problem.
Yeah, because at low densities, if you take the low density limit, the radial mode is going to.
Right. Yeah. No. Absolutely. This is all large charge stuff. And I should say, by the way, there are cases, where this genericity argument fails due to accidental symmetries at large charge accidental symmetries. So those do exist, and there are now a couple of known examples. The easiest example is in 2 dimensions, where along the flow, the only symmetry you have is the U1, but then in the infrared you get an enhanced Kac-Moody symmetry. Right? The entire UN current algebra, and you really get a different universality class because of that. And then there are other examples involving line operators worked out by Kamargatsky, Como, Raviv Moshe, and Mizet, and other people like that. Possibly some names I'm forgetting. Sorry, guys. So, but these people did many interesting papers like those. And so this is another case in which it turns out there's a kind of decoupled, strongly coupled sector. So there's an accidental symmetry where you kind of have 2 decoupled sectors. They each have their own little stress tensor. And you have one small bit that decouples and another large bit which is perturbatized by a sort of large charge expansion. A large level expansion in your case, but that's large charge in the defect. So even these genericity arguments can fail because there can be accidental symmetries you didn't foresee, right, at the beginning of the argument. So I think, to really answer it, you have to just do the analysis case by case, but it's always accessible, by just running the argument.
Any more questions for Simeon?
Da, let's thank Hellerman.